still don't have my voice. So today we will just keep the recording, and if you have any questions throughout, you can put it in the discussion on as you learn, and I will answer it as soon as I can. Hopefully I'll have my voice back by Wednesday. A few announcements. I will still have office hours, so I can still do one-on-ones. It's just in a large group. I can't really use my voice. If you want to pick up your exams, you can come to my office hours or schedule an appointment. I will be keeping the Scantrons, so that way you don't have to lose them. So if you didn't write your answers on the exams, you can come by, look at your Scantrons, and put them on your actual paper copy. The two most missed questions were based on sig figs and ion charges. So one of the questions had you do multiplication and addition in a specific order. You do have to actually work it out. You can't just use the values given, because what happens is you lost a sig fig when you subtracted. So remember that for adding and subtracting, you have to use the lowest amount of decimals. With multiplication and division, you use the lowest amount of sig figs. So in adding and subtracting, you can gain or lose a sig fig. So pay attention to that. As for ion charges, remember that in neutral elements, the number of protons equals the number of electrons. However, once you have ions, those numbers are not equal. In cations, where you have a positive charge, you lose electrons. But again, the number of protons stay the same. In anions with negative charges, you gain electrons. And again, the number of protons stay the same. So I think that confuses some people in that. As for chapter 7, I'm hoping we can finish it this week, but given my lack of voice and the ability to cover a lot of material, we might have to push it back. So pay attention to the due dates and due times of your quiz and your homework. There were some issues last time, even though I made announcements in class about the due time. So don't just look at the date, look at the time also. Okay, so we don't have a clicker question because we're not here. But this is covering material that Dr. Cecil covered on Wednesday, and also what you should have covered in lab this week. So in this case, we are looking for the wavelength in nanometers associated with an energy. And Wednesday, you learned two equations. You know that the energy of a photon is equal to the frequency times h, which is just Planck's constant. But you also learned that frequency is equal to c over lambda. And I hope Dr. Cecil told you the joke. It's one of my favorite jokes, but if anyone ever asks you, hey, what's new? You reply, c over lambda. I love that joke. Anyway, so we have two equations that have frequency in it. So we can sub in this equation. So we can sub in this equation into E equals nu h, and we get E equals speed of light times Planck's constant over the wavelength. Now, this equation is not asking for energy, it's asking for wavelength. So we can rearrange this equation and solve for wavelength, where the wavelength is equal to c over h divided by the energy. And we have energy, and we have speed of light and Planck's constant. Now, all of those are already in the needed units, so we can just plug and chug. C and H are constants. E we have here. you keep the positive and negative exponents and pay attention to those and make sure you don't mess those up because you'll get a really weird number. So when we plug in, we get a wavelength in meters. But the question's asking the wavelength in nanometers. So we know from our our conversions that you've had memorized that there are 10 to the 9th nanometers in 1 meter. So if we do the math, you should get 303 nanometers with correct sig figs. Okay, because we have 3 sig figs for the speed of light, 4 sig figs for Planck's constant, and 3 sig figs here. Okay. So, and what you learned from lab is that this energy produces what we call the emission spectra or atomic line spectra. And this is based on the energy of light being absorbed and emitted. And each element has its own spectrum. So in lab last week you learned that you can identify neon and what else? I think mercury and copper and lithium, and you saw that each of those were very different. Some of them have the same color, visible flame, but when you look through the spectroscope, you saw that each of those had different lines. And how do we get those? So the theory behind that is based on absorption and emission energy levels. And we learned that hydrogen, which has 1 proton and 1 electron, has the simplest form. So has 1 electron. So if it has 1 electron, how do we get multiple lines? I will cover that in a second. But the theory behind it was found by J.J. Palmer and J. Rydberg. And what we see is Rydberg found a formula to predict the spectral lines. And here what we see is the equation. And make sure you pay attention that this equation is only able to predict hydrogen. Okay. Now these ends, what you learned from the class on Wednesday is that these lines respond to N, which is the, let's see if I can bring this over. Is that gonna come over? Nope. There we go. The energy state, so the ground state to the excited state, and we call these states N1 or N2, and they can have multiple excited states, so N3, N4. Let's bring that back. No, actually, let's see. So when you put energy into a system, your electron gets excited to these states. So even though you only have 1 electron, you can have multiple excited states. And that means that electron can go in different locations. So the number of electrons does not correspond to the spectral lines. It's the state numbers, or the excited states, the number of excited states that correspond to the number of spectral lines that you have. emitting electron. You're going from a low number to a high number. If you're emitting, then you're going from a high number to a low number. And Dr. Cecil should cover that on Wednesday. So in this case, n1 and n2 are whole numbers or integers from 1 to infinity. And that corresponds. So n1 is a ground state, and then anything above n2 is the excited state. So you can use this to find the wavelength to explain the spectra for hydrogen. So that equation predicts the spectral lines within the visible region, but also the spectral lines that we can't see. So we learned that the electromagnetic radiation spectra is more than just the visible line, right? Or the visible spectrum. You also have IR and UV. And that we can't see with our eyes, but they're still there, and there's other ways you could detect them. Now, visibly, what does that mean? So when we talk about absorption, in chemistry, we sometimes get a little bit lazy, and we just put them in the lines like this. However, that visibly what this means is we learned about the Bohr model, right? So the Bohr model has these circular or spherical orbitals here. And so what happens is the electrons in the innermost sphere gets filled up, and as you increase the amount of electrons, then the second one gets filled up, and then the third, and so forth. And so the electrons can move and jump. But again, the energy levels are quantized. So that means they can't just jump anywhere. So you're not going to find an electron in space here. You'll find them on the lines. So I think Dr. Cecil represented this by going up the stairs in the classroom. You can't go in between the stairs, but you can go from one level to the next level to the next level, which is a lot different than going up a ramp, correct? Where all the energy is continuous. Here, they're quantized. So if an electron jumps from a lower level to a higher level by inputting energy either through heat, so like flames that we did in lab, or through electricity, like the emission tubes that you saw in lab, that jump is called absorption. When it's in an excited state, it's not very stable, so it doesn't want to stay there for very long. And so when it goes from a higher level to a lower level, it emits, and it emits in a form of light. Now, sometimes that light is visible to us. Sometimes it's only visible to in a way that we could detect through instrumentations. So in order to find the energy change, you go to energy of the highest minus energy of the lowest.